We're going to talk about water and its solutions. If we look at water, we realize that it has some really unique characteristics for a molecule its size. It's the only substance to exist in large quantities in all three states of matter. Its solid is less dense in its liquid form, and it's liquid at room temperature. So here we can look at some molecules that all, if you look here at methane, ammonia, and water, they all have similar molecular masses. Methane and ammonia are gases at room temperature. Water's a liquid. You can see the huge difference in the melting and boiling points as well. And then you have nitrogen and oxygen, which both have larger molecular masses than water. And you can see their state at room temperature, their gases, and their melting and boiling points are so much lower than water's. So water, because of its hydrogen bonding, has a lot more strength than other molecules its size. We talked about polarity and bonding, and we know that the dipoles, so here we have water, and you have your negative dipole and your positive dipole. They act like magnets. They're not just for structure and organization to the two attractive model, but or molecules, but every molecule affected by these dipoles in water. It's like a magnet with a series of paper clips. You can pull up, you have the magnet up here, and all these paper clips get pulled together based on the strength of the magnet. So this dipole affects every single molecule around it. It's actually pretty neat. That hydrogen bonding, as we talked about when we were talking about polarity and molecular geometry, occurs in molecules through the attraction of a highly electronegative atom like oxygen, fluorine, and nitrogen to hydrogen. So if you have oxygen bonded to a hydrogen, you're going to have that dipole. If you have hydrogen bonded to a fluorine, you're going to have that dipole as well. And it's going to be the same with nitrogen. Although oxygen is going to be stronger than nitrogen and fluorine will be stronger than oxygen because of the electronegativity value here. Now, the hydroxyl groups, the OH groups in molecules, tend to promote intermolecular hydrogen bonding. So between molecules. So you have your negative dipole here and your positive dipoles on each of your red hydrogen atoms. Now in pure water, each water molecule can bond with four others. And you can see here, you have 1, 2, 3, 4 of these bonds, of these hydrogen bonds between these little purple rectangles are those hydrogen bonds between water molecules. So each water molecule can bond with four others because these lone pair of electrons that are right here, they are each a negative dipole. And they bond with hydrogens around it, which are the positive dipoles. Alcohols can also form hydrogen bonds as they also contain the OH bond. It's not going to be as strong as water because it has more carbon chains in it, but it could still form hydrogen bonds. So alcohol and water can mix together because of that. Proteins, nucleic acids, and carbohydrates also have the ability to form hydrogen bonds. So in our biochemistry, in our bodies, hydrogen bonds play a really important role. So let's talk about some of water's physical properties. A lot of them are the result of hydrogen bonding that occurs. Water's primarily a liquid at room temperature. Because the hydrogen bonding is so strong, it can prevent the molecules from readily escaping into the gaseous state. And that's why it has a high boiling point. It needs a lot of energy to break those bonds. The hydrogen bonds have to have an increased temperature to break them as they are so strong. If we look at the density of water, we can see that as the temperature drops, so here we're at room temperature, 20, well, this is 30 degrees Celsius, which is a little bit warmer than room temperature. But as it cools, you can see that the density starts to get bigger and bigger and bigger and bigger. And so whenever it freezes, and then it starts to decrease. So as water freezes, its density decreases. So it floats on top of its liquid form, which is actually really unique. Most solids are more dense than their liquids. Now, liquid water does shrink and become denser when it's cooled, but at a certain point, it starts to expand. But as it cools from 60 degrees Celsius, which is much warmer, it's not quite boiling, but it's very hot water, its volume starts to decrease, and that does increase its density. But when it gets to about 4 degrees Celsius, the volume stops decreasing and it starts expanding. And as it expands, it decreases the density. The decrease in density is due to hydrogen bonding. Now, we've all seen cracks in sidewalks. What happens is water particles get into small cracks and it freezes. And as it freezes, it expands and it pushes against the concrete and it will expand those cracks. It could freeze your pipes. I remember I grew up in West Virginia, very, very cold in the winter sometimes, and we didn't have central heating. Sometimes whenever it dropped into the negative temperatures, my mom would be up and using the hair dryer on the pipes that were on the exterior of the house because she was afraid that the pipes would burst. We'd have our space heaters and our gas heaters and our fireplace going, but she didn't want our pipes to break. I also noticed a small chip in my windshield once, and it was winter, and I thought, oh, I can't get to it today to get it taken care of because you could get a small chip patched. I'll get to it within the week. And unfortunately, we got snow, it froze, and my small chip turned into a large crack that was too big to patch, so my whole windshield had to get replaced. Capillarity is the rising of liquid into narrow tubes, and we call this capillary action. So if you get your blood drawn, sometimes if you do a finger prick, they'll take a blood sample and it'll just be pulled up inside this little tube. It's called a capillary tube. And then you have a little sample of blood there. It's called a capillary tube because it just naturally rises up. this is what happens in our own capillaries and in the roots of trees and plants. This is how plant life takes water up into itself and why blood rises in the capillary tubes. We're going to stop there and we'll see you next time.